started?
Papa. Yes, sir.
Trying to get this present to be on.
Yes, sir. Please go ahead.
Okay. All right. Thank you. Thank you,
Okay, so
Kritagya,
let me
for
introduce you first
yeah.
and then we'll start.
Yeah,
Okay.
sorry.
So, yeah, no problem. Sorry, sorry. My daughter is with me, so she is asking me constantly some questions and so on. So with her, we'll start. Just a minute, bacha, just a minute. Okay. 1 minute max, just 1 minute. Okay. Okay, so welcome everyone to this ICWaR seminar. And we have today with us Dr. Sanket Jantre. He's a research staff at BNL. And BNL is a very famous laboratory doing, I think, phenomenal work in terms of AIML. And I think if I know very well, then a lot of fundamental work is also being done there. Uh, and he is a Emmy author postdoctoral fellow. And he has held a staff position since 2024. He has a PhD in statistics from Michigan State University and has a dual BTech chemistry degree in CS from IIT Kanpur. So with this, I think he has done a lot of work in Bayesian statistics and scientific machine learning. And today he will basically talk about Bayesian learning about Antarctic ice sheet dynamics and sea level rise. It's a pleasure to have you, Sanket. Please, the floor is yours. We expect around 35-40 minutes of talk, followed by some interaction. So, yeah, please start. Thank you.
Thank you, Dr. Vishwakarma, for the kind invitation. It all started from your project assistant, Kritagya, who reached out to me about one of my papers, and I asked him whether I could present our ongoing work or like the one work that we have submitted recently. And today I'll be presenting both the previous work, so we have like a nicer transition on why exactly we chose to do or pursue the present work. So this Bayesian learning, this is one of the major areas of research I work here at Brookhaven National Laboratory. Perhaps I should also mention these rings that you're seeing behind this slide. This is the Brookhaven National Lab, actually, and that is a light source. It's one of a kind light source here at the lab. And behind on this top left corner, you'll see one hidden behind trees, a very large circle. That's the accelerator or like collider, very famous, and it is like of comparable performance as the CERN one. So they collaborate a lot, CERN and this electron ion collider, which is upcoming, and the relativistic heavy ion collider is the previous one. So that's a little bit about the Brookhaven lab and why it is famous, and especially the department I work in, we work on uncertainty quantification, Bayesian statistics, Bayesian machine learning, optimal experimental design, optimal control, all sorts of different problems. And then we try to apply to several areas such as material science, climate science, life sciences. And this is one of those areas where we are applying Bayesian learning to Antarctic ice sheets and trying to learn the dynamics as well as the future sea level rise that may arise out of it. And this work started when I joined as a postdoc, and then I mentored one of the undergraduate students for the subsequent paper. So these are the two papers. So let me move on to the next slide. So I think we all know Antarctica is a large source of sea level rise uncertainty that may arise by end of century as well as like many more years to come afterwards. And it is the largest source of uncertainty on century time scale. So up to year 2100, that is the largest contributor right now. And the Antarctic ice sheet disintegration is like most strongly influenced by the stability of floating ice shelves that are coming out of the land ice mass that is sitting. And this is one of the phenomena which is causing the instability, what is called the marine ice sheet instability. where your glacier is on a retrograde slope, and as the grounding line is, let's say, retreating inland, then you have like more and more instability because you now have larger column of ice that is like straining and causing more melting to happen. And it is believed that it is already has started in West Antarctica. That tends to be a very unstable region compared to East Antarctica. And for us to study this, we usually rely on high resolution numerical modeling to predict how this glacial retreat is happening and how fast, and what are some factors that are causing it, and what is the dynamics underlying it. So today we're going to focus on mainly Amery Ice Shelf Basin. This is part of the East Antarctic region compared to West Antarctic, and it drains the Lambert, larger Lambert Glacier Basin, as you can see here in this picture. It is the largest glacial system in East Antarctica and third in Antarctica. It has 16% of grounded area there. But as I said, East Antarctica is largely stable than West Antarctic region. And a stable glacier, perhaps less interesting from the perspective of near-term sea level rise, but a good modeling test case. So when we are fitting complex models such as Bayesian statistical models, then we want to make sure at least the numerical model underlying it is more or less stable on century time scale or slightly further beyond. So it would be easier to initialize into like a realistic present day configuration versus we did start out with weights, but it was really hard to get it into like initialize into a realistic present day configuration. And this Mali MPAS-Albany Land Ice model simulates this Amery Ice Shelf region. It is part of the U.S. Department of Energy's Energy Exascale Earth System model, which is a coupled global Earth system model, which also has atmospheric component, ocean component, and this ice sheet component as well. Lots of this is a very flagship model, and my collaborator is the developer of this particular ice sheet model. This is a 3D numerical ice sheet model solving the first order Stokes approximation, later pattern. And we have this optimized basal traction, ice stiffness. We also have unstructured mesh. So as you have more dynamic region, you have like high resolution, and in more inland where you don't have as faster moving pieces, then you have like low resolution mesh there. And we have like evolving ice temperature and also the calving law. And even to simulate, let's say 200 years of simulation, it takes 10,000 on the orders of 10,000 core hours. So it's not feasible enough to be ran for Bayesian statistical learning, because we ourselves, when we are inferring or calibrating the parameters that are driving this numerical simulation, we have to do like what is called Markov chain Monte Carlo sampling, and it might take like hundreds of thousands of the samples, and in each sample to evaluate what is called likelihood, we might have to rerun this numerical model. So we have to leverage faster and cheaper statistical models that could kind of emulate the numerical simulation that I will talk about. So first of all, in our first paper, we took a 200-member ensemble of simulations. So even to create a statistical model that could emulate the numerical model, we need certain number of high resolution or high fidelity simulations to our disposal. And then only we can fit our statistical model to them. So we are probing our 6-dimensional input parameter space, which consists of these basal slip exponent, basal friction. We also have ice stiffness, calving yield stress. We also have melt coefficient and melt rate. These parameters. What we do is this Sobel's quasi-random sampling, which is uniform space filling design, and over certain min-max parameter range. So the glaciologists gave us this should be the physically plausible range for the 6 parameters, and we went in and did uniform space filling sampling so that we are covering all the possible states and not just a random sampling, uniform random sampling, because we want to make sure every area gets like nicely sampled over here. And Sobel sampling method has another nicer property compared to Latin hypercube sampling, is that you can, even if you started out with, let's say, only 100 member ensemble and you realized 100 member ensemble is not sufficient to capture the numerical model's dynamics quite well, then you can go back and incorporate another additional 100 without breaking the space filling property of the earlier 100 ones. So it keeps on including more members. And so for that adaptive property, we ended up using that. We have this ensemble try to be like brought to the present day, like this initialized to the present day configuration. And you can see how the calving front is moving. And some of the runs, they after a while, they tend to break. So you have to monitor them quite a lot. Even if you have like a 200 member, it does take a lot of time to make sure we have a nice, plausible ensemble, which was also the problem we faced in the Thwaites Glacier. And this is just a residual error in ice speed for 8 runs at the end of spin-up period. So this was all done by the glaciologist giving us the numerical simulation, and we were the ones who were doing the Bayesian calibration and uncertainty propagation work. So let me talk a little bit about what is statistical emulation. So we are trying to fill out an ensemble, a small ensemble. So right now we only have 200 member ensemble, but there could be infinitely many possible choices for this 6-dimensional input parameters that could be used to initialize your numerical simulation. And as I mentioned, it is a very expensive computer model, and we cannot afford to run it for 10 to the power 5 times to sample any tail area probabilities. We only have hundreds of runs. So can we estimate what the model would have predicted at new parameter setting without actually having to run that model each time? So that's where this response surface modeling comes in. It's a non-parametric regression approach. We do not assume a functional form of that curve. So doing, let's say, a polynomial regression, let's say fitting a quadratic curve or this third order polynomial curve, then you already are setting in stone that there are only 3 parameters, 3 free parameters that you are able to tweak around and optimize for. But in non-parametric regression, the functional form is already not assumed. So we choose to use that. So it's just like a nice smooth curve fitting. There's also lowest regression or something. But in this particular case, we ended up using Gaussian process emulator. As you can see, like we are the Bayesian statistics people, so we needed with our predictions the uncertainties, and Gaussian processes have this nice their probabilistic nonlinear interpolants of outputs over input space, and they estimate their own approximation errors, and they also work quite well in small training sets. Since we only had like 200 member ensemble, we chose to work with Gaussian processes. So only few hyperparameters to tune. And in our case, we have three observables of interest or outcomes of interest. So we trained three scalar Gaussian process emulators because those three observables were independent of each other. So we didn't have to go in and try to do any multivariate type of Gaussian process emulation there. So this is just an example where a Gaussian process is going to give you like a predictive mean. On the right, you can see it is the blue line that is sitting in between the band. And as I said, we are getting emulator prediction as well as the uncertainty interval around it by using this probabilistic Gaussian process emulator. So you'll see we are using that all over this work. So first of all, we also want to make a sanity check, how good this Gaussian process surrogate is actually emulating the Mali ice sheet model. So what we saw is the residuals that we get from this regression are nicely spread around the zero line, the horizontal zero line in this the top left plot. This is the residual versus fitted values plot. Quite common in linear regression modeling, if you have seen. But here, even for any regression modeling, you want to make sure these residuals are like a nice scatter plot around zero line, as well as we have prediction versus true values. They're sitting very close to 1-1 line. And you may think the uncertainties around them are not too big. So we also in paper include this additional plots where we look at like if we have like 5% intervals, 10%, 50%, 95%. So if you plot 95% interval around your predictions, you want to make sure only 95% of those intervals capture the true values, or like 50% interval will capture 50% of the true values. And that gives you like a nice plot of like emulator validation, which we include in the actual paper. And here we are sure that these surrogates are accurately emulating the Mali output, and they're not too overconfident or underconfident. So once we have these scalar Gaussian process emulators in our Bayesian calibration workflow, where we are doing Markov chain Monte Carlo. Specifically, we are using no U-turn sampler, Hamiltonian Monte Carlo, and trying to do this 100K samples post-burning, where we use these Gaussian process surrogate models to cheaply and quickly do the Bayesian inference over the input parameters of the numerical model. So these are the numerical model parameters: the calving yield, basal slip exponent, we have Bayesian friction scaling, ice stiffness scaling, melt coefficient, and melt rate. So what we observed was some parameters are constrained by this present day data, and others are not. So we have what we call year 2015 actual observations. And those three observables, as I mentioned, calving front position, there is mass balance and grounding line position. Those are the ones used to constrain these input parameters using Bayesian calibration. And what we observed, some of these parameters are constrained, which include this calving yield, basal friction scaling, ice stiffness scaling are getting at least nicely constrained. And we also observed, what if we only used one of these observables to constrain these input parameters? And in some scenarios, they did not constrain some parameters, like this posterior with mass change did not constrain calving yield. But when you incorporate all of these observables together, the calving yield was nicely constrained. And also these three parameters are nicely constrained. Melt rate is constrained as well, but not as good. as you would like it to be. And same with basal slip and melt coefficient, they are not constrained by just present day observations. So that's one of the motivations for our subsequent work for including future observations. So let's move on for the what we do with this calibrated input parameters. So now you have like today's observations constraining the input parameters, and now you would like to sample out of these calibrated posteriors and then propagate them through another, like again, numerical simulation ideally, and project out and check how the sea level rise would be, the actual sea level rise projections would be. But again, running these numerical models would be too expensive. And for sea level projections, we have actually a time series of data going from year 2015 or year 2016 up to year 2300. That's the period we chose to look at how the sea level projections are going to be. But there are since 285 observations sitting in time series. How can we like again cheaply project these input parameter uncertainties into this sea level rise projection uncertainties? So we choose to do emulation, again statistical emulation of time series data to generate future sea level rise projections. And for doing that, what we do is apply dimensionality reduction. Since this is the time series, it's going to be very correlated amongst each other. All these, like year before, let's say 2030, 2029 is going to be correlated with 2030 as well as 2031. So there's like lots of correlation, autocorrelation going on since with the time series data. So we applied this dimensionality reduction, and only 5 principal components were sufficient enough to capture 99% of the variability in your time series. And as you know, principal components are orthogonal to each other, right? So they're uncorrelated to each other. So we can fit 5 separate Gaussian processes and combine the predictions from each of them and project it back into the full time series space. And same you can do for its covariance. So you have individual variances you can combine and make it into a 5 by 5 matrix, which will be projected back into the 285 by 285 matrix for the covariance matrix. And that's what we do. We mention this procedure in detail in the paper. And here we just wanted to do a sanity check for, let's say, just one single individual year. So this is year 2300 on the left side plot to make sure it is doing what it's supposed to be doing. And we also wanted to make sure, let's say you have this actual simulations, right? We had the 200 member ensemble, and we wanted to like just propagate the actual 200 member input parameter ensemble via this time series or like multi-output emulator and check whether they are closely matching. And we see they're like very close to each other, these projections, like the predictions are comparable to the actual ones. So once we have validated that our PC emulator is doing what it's supposed to be doing, then we go on to actually project out both prior uncertainties and posterior uncertainties. So in prior, our glaciologists had told us, oh, these should be the physically plausible distributions over the 6 input parameters. And we went in and constrained them using present day observations, and we got the calibrated posterior distributions, right? So we want to check whether it impacts the sea level projections anyhow. So what we saw is prior samples lead to slightly wider intervals, especially the lower bound of these projections for this 95% credible interval. Now you can see for our posterior uncertainties, when we project out what we call as posterior predictive distribution, this interval has slightly narrowed, especially on the lower side. So it is indicating that sea level rise is going to happen. So it's going to be non-zero because the zero is not included in that 95% credible interval. And it could be substantial as well. So the mean earlier was slightly lower, but it is slightly higher here. So it is indicating that by year 2300, you'll have sea level rise. Of course, up to year 2100, we did not observe that there could be any like sea level rise could be happening. At 2115, there's like a very rapid change where like entire ice sheet just rapidly goes into the ocean, and that kind of triggers this rapid sea level rise. And that is you are seeing here. And we also wanted to have a sanity check whether each of them are like capturing this overall distribution. And the distribution is not just something like averaged mixed map of this like individual projection. So these distributions are calculated using 10,000 samples, which would have been infeasible to do so using just numerical simulation. And for decision makers, they're more care about like specific years, like 2100, 2150, or 2200, or 2300. So we also, what we did is we went back and only trained scalar Gaussian process emulators for those individual years for projecting out the uncertainties, and then plotted the sea level rise. And as you can see, for year 2100, 2150, we do not see any tangible sea level rise happening. But by year 2050, as well as 2300, we see that there could be substantial sea level rise, even coming from very stable, previously thought out to be very stable glacier. But now that we have projected it out to year 2300, we see that there could be some sea level rise. And we also wanted to check whether it is due to high emission scenario. So we included SSP5. Now IPCC has disregarded SSP5 being too unrealistically high. So SSP1 is still quite low emission, so world is still on a higher level, but there's heavy adoption of like renewable energies and all, and they're becoming cheaper, and world is not using as much coal. It's moving towards natural gas. So SSP5 is very unrealistic, but we used it in this paper to see what might have happened. So the control ensemble, we saw a negative drift in control because these historical runs were not fully in equilibrium with the historical climate conditions. So that added certain drift. And this low emission scenario kind of mimicked that drift. So when we take out that effect of a negative drift, we can see that low emission might not cause any sea level rise, or in fact, any sea level decrease, let's say, for this emission scenario, because it is going towards like a negative side. And even after accounting for this negative drift, we see that this high emission scenario will still have substantial sea level rise. So now there were like few interesting observations that we made during the rebuttal for this paper. This reviewer asked us to do sensitivity analysis, and here we did that, where we are like taking certain value for each of the input parameters and conditional on that specific value of the, let's say, calving front, we choose 1 as this value, and using that, conditional on that, we sample from the joint prior distribution of rest of the parameters. and look at how would it have projected out into the sea level rise uncertainties. So this is just very thorough sensitivity analysis, since we only had 6 scalar input parameters. So despite being constrained by data, calving yield itself did not affect sea level rise. And in contrast, basal slip exponent, as you can see, which was not constrained by data, had the largest impact on 2300 sea level rise. So these were kind of like intriguing observations that we made. So basal friction and ice stiffness have also similar effect on sea level rise. So what could be happening? It might be that the data itself that we use to constrain these input parameters might not have been as informative, or just present day observations were not enough to constrain these parameters, So we thought it is worthwhile to investigate what might be happening here. So the Amery Ice Shelf is near stable today. So present day observations carry little dynamical information. And the basal slip exponent, that is Q, controls the glacier's nonlinear response to a loss of buttressing. That hasn't happened yet. And as I mentioned, the year 2150 seems to be the critical year when suddenly there is a very much like a dynamical, lots of change in dynamics happening there. So that may be the one reason that we are not seeing it being constrained right now. Why the future is different, as warming thins the shelf and grounding line is beginning to retreat, the dynamical response should imprint on observable mass change, turning like the slip exponent from unlearnable to learnable. And that's what we see happening in our subsequent paper. And why should we care about this timing? The rate at which these uncertainties shrink is itself decision relevant. So fast learning supports a wait and see posture. And slow learning argues for earlier precautionary action. That was part of my supervisor's paper back in 2014 when he did this future learning type of study, value of information study. And how we test it? Sequential Bayesian calibration. So feed in synthetic future observations year by year and watch the posteriors and parameters as well as the projected sea level rise contract. So how quickly can these additional observations reduce uncertainty, right? So these glaciers often respond slowly to climate change, decades to centuries. So with caveats about being like the fast ice dynamics, like when you have this marine ice shelf instability or ice cliff instability, or there's hydrofracture happening on the surface. So except those, you'll have like very slow periods of any changes. So how long will it take to learn more about glacier dynamics? We don't know for sure. So this is where this value of information study comes into picture. What is the expected future rate of uncertainty reduction that may happen if we keep on adding or feeding in more observations? For that, then we simulate these future observations sampled from current uncertainty distribution. So what do I mean by current uncertainty distribution? Is the present day posterior distribution. So that is from my previous paper you saw. So we just sample out of that. And we choose an observable that was nice enough in our case. So we did not choose to use the same observables that we used in our previous paper because they were instantaneous rates instead of like some cumulative metric. And we observed those instantaneous rates tend to be very noisy and harder to statistically emulate compared to cumulative metric that is more smoother. So we use cumulative grounded mass change variable for future the sequential calibration study. So going back, we are going to treat these simulated future observations in the middle as our additional measurements. and we'll keep on updating posterior. So as you can see, this present day posterior in black, and you'll see these future years um, posterior distribution would be shrinking towards the parameter values that we use to sample those future observations. And it will become more clear as I go on. So we have this Bayesian learning update the posterior using future data. So we are pretending in this study that we have continued observing up to year 2030, up to 2075, 2020, so up to year 2300. So as you can see, at new observation is being taken at every 15 years. So we choose a very uniform interval, and we end up with like almost, I believe, 18 in total future observations from year 2030 up to year 2300. So let me play this again to, let's see if I can. So this is how like each windowing could happen. And we can sequentially then calibrate our input parameters as more data comes in. So the longer data set, present day plus future up, to like, let's say some certain target analysis here will reduce parametric uncertainty. So again, pretending we have more observations, what might happen, we are going to redo the same Bayesian inference and update the posterior with data up to that target year. And here I just present one such future observation trajectory and what happens to the input parameters, how much they get constrained. And let's see, we have year 2030 come in, then we have another 2 years come in. So you can see these uncertainties are reducing. The posteriors are contracting towards these black dash dotted lines. These are the lines that represent the actual input sample from the present day posterior that was used to generate the future observation trajectory and then perform the sequential calibration. So these posteriors need to converge to that actual parameter draw, So, and we saw that happening. So even using just present day posteriors or like the present day observations, we were not able to constrain some of these input parameters. But when you add more future observations, we tend to see that these posteriors are converging towards those nice parameter draws that were used to generate the future observation trajectory. And learning trajectories show how uncertainties reduce over time. And now I show like how these cumulative grounded mass change observation trajectories that we had generated. So these represent, I believe, 8 or 10 out of 100 trajectories that we had taken. And we just wanted to see how these uncertainty bands would reduce over time for 4 of these, let's say, input parameter draws, or like these 4 future observation trajectories. So some of the parameters, these uncertainties reduce nicely, and some others, they are still overlapping. So there is not much uncertainty reduction. And even if there is uncertainty reduction compared to year 2015, that is the present day, up to year 2300, since the bands are still wider, we are not able to see much difference here, like for calving stress or basal melt rate. But the slip exponent, if you remember, was not getting constrained before, is now getting nicely constrained here. So that's one big benefit of going from previous work to this work, that we saw like adding more observations in future ended up constraining this basal slip exponent. So we are just, as I said, choosing 4 future observation trajectories and seeing how the posteriors contract over time, and plotting as a narrow band of uncertainty here. And again, these are converging towards the true value. That's why we have plotted the mean, the posterior mean, and checking whether it converges to that value overall. And it seems to converge there nicely. And most learning occurs after 2150 because the warm water intrusion accelerates that retreat and making it unstable, and a rapid loss of ice shelf happens then. Now, I want to take at an overall picture, the 100 future observation trajectories altogether, and look at the uncertainties only. So what we do here is, we are going to look at now across these 100 trajectories, what is the credible interval width? Because what we cared about is whether these posteriors are contracting or not. So we care about these uncertainty bands around them and how quickly they're going to contract, if that makes sense. So we ended up plotting this 90% credible interval width. What is this width and how quickly that width is decreasing? So width always going to be at least 0. So we ended up choosing the lower axis level for this y-axis to be 0 to put them on equal footing. So you can see which parameter have like the really high learning. And here basal slip exponent as well as this gamma naught parameters, the melt coefficient had like the highest learning, versus calving yield and melt rate had like moderate learning. So as I said, we are collecting better statistics over 100 future scenarios, and we are looking into this uncertainty bands, how quickly they're decreasing. But since we now have 100 such future observations, we can use them to even calculate uncertainty in the uncertainty, because we are plotting uncertainty bandwidth. That is our first uncertainty, first layer. And on top of that, since we have such 100 future observation trajectories, we end up plotting uncertainties over uncertainties. So these essentially indicate these shaded bands are the 100 such scenarios taken together and plotting their like 66% credible interval. We end up choosing 66 and 90% to stay close with what IPCC uses in their reports. So what we observe here is forcing drives this early learning and ice dynamics drives late learning. So learning is very much parameter dependent. This melt coefficient had like 10 times uncertainty reduction, and basal slip exponent had like 8 times uncertainty reduction by year 2300. Others had modest. Melt coefficient learns early as ocean forcing rises, and this drives ice shelf. So this you can see sudden drop in this gamma naught parameter here. And basal slip exponent learns late. So after that dynamic change at year 2150, that's when the basal slip exponent is rapidly learning. Most of it, or like these uncertainties are contracting. Now, we have these parameter posteriors from the sequential calibration at each of these individual analysis years. And what we could do is go back and use the sea level rise that how we projected using this multi-output emulator, and use that emulator to project out these constrained parameters to get the posterior predictive distributions or sea level rise. And we wanted to check that for specific years, year 2100, what happens, year 2200, and year 2300. So again, propagate parameter uncertainties to projections farther beyond the analysis year. So for example, if observations were continued until year 2065, what would be the uncertainty in sea level projections for year 2100? So to get the year 2100 sea level rise, we are only going to look at the analysis years up to year 2100. So that's why you see it ends at 2090. The leftmost plots, x-axis ends at 2090. Same at 2200 sea level rise. We are only going to look at analysis years that precede the 2200. So that's why the ending is happening at 2195, because that was the analysis year we chose for sequential calibration. And we have the constrained parameter uncertainties that we can project out to see the sea level rise in 2200. And same goes for 2300. So we will still have some model errors left, and there are like approximation errors. So you're not going to see overall uncertainties reduced to 0 by year 2300 or something. We haven't accounted for other input parameters as well in this. So that could also drive the leftover uncertainties here. And from this particular predictive uncertainties, what we learn is sea level rise in 21st century. We are learning nothing much. It's not much happening. But also you can think about is sea level contribution at 2100. Those bands are going from -3 to +3. So that's not much sea level rise there. But as you go to year 2200, observations through 2050 to 2075 reduce the uncertainties quickly, and then they stay almost similar for subsequent years. And for 2300, we have the same, that year 2115 and 50 and onwards. Once that dynamic change happens, you have like more and more uncertainty reduction. And Bayesian learning about the sea level rise, we are expressing now as interval width over time. Again, we had these 100 future observation scenarios. So we can also create these uncertainties and uncertainties. By that, I mean the uncertainty in the credible interval width and plot it out. And that's what we do by using this 66% credible interval across this mean value, and also plotting individual trajectories to see how the credible interval band is reducing. As again, I mentioned, we do not observe much learning happening at year 2100, but 2200, it has that early learning from 2050 to 2075. And year 2300 sea level rise has late learning after that dynamics change happens. We have that rapid learning period happening. So what we can learn about SLR depends on the projection horizon. Year 2100 barely tightens, 2200 6 times reduction tracks log gamma naught. So that melt coefficient is the one that is helping that reduction over here, and it tracks that parameter well. And 2300, almost 6 times reduction, tracks Q, the nonlinear response to lost buttressing. And that's what we discuss in our paper in the discussion section. Which parameter you can learn and when depends on the time horizons. But still, in overall this study from previous paper, this paper, there are some key caveats. We are doing this perfect model assumption. So synthetic observations are coming from the same model we calibrate, and real structural errors would slow the learning. And with this big models of complex systems, we also have model misspecification errors and such. We also have single observable post 2015. So beyond present day, we are only looking at this cumulative metric of grounded mass change. A richer spatial data like basal friction field or something else could improve or could learn faster, but might make Bayesian inference time consuming or intractable even. And single GCM plus scenario, this is a very high emission scenario. As we mentioned, it is already disregarded by IPCCs. So likely a best case of learning for us, but still not going to be informative now in today's emission scenarios. Sorry. The conclusion, the uncertainty quantification naturally leads to the question of what can reduce uncertainties further. So we can collect more data, collect better data, or collect different kinds of data. So that's what we are doing, this value of information study. What if we added, what we might be learned by collecting data over longer period of time. And the procedure itself involves simulating the future observations and redoing the uncertainty quantification workflow on hypothetical measures. And because of the slow response, little learning about this ice system is possible this century, year 2100. So something needs to happen like the 2150 scenario that I mentioned. That could cause significant mass change and leading to significant sea level rise. And data collected toward the 21st century becomes significantly more informative about what will happen in 22nd century instead of year 21st century. And future work, we can study other faster responding glacier systems like West Antarctica. That's our goal. Or if not that, then entire Antarctic ice sheet is the goal for the final year of the project. And add more observations that could involve like other variables or spatially resolved measurements. So currently we are also looking at what if we added like this basal friction field uncertainties even in this uncertainty quantification workflow. And also how can we design a better system itself? So optimal experimental designs setup could be helpful in this situation. So yeah, that's mostly my talk. Thanks for listening. And I'm happy to take any questions. Sorry for running over time.
Yeah, very nice work, Sanket. Really enjoyed the work and the introspection and the inferences that you brought together. So I think it is time for a few questions. Anyone is interested to ask Sanket? Or otherwise, I can start the discussion and maybe in the flow of the discussion, others will also pick up. So Sanket, as I understand, emulators have a known problem, not only your emulator or my emulator or other emulators are known problem that they are as good as the physical model. So they can, so they can emulate. In fact, if there is certain incompleteness, just as a general term in the physical model, that also gets emulated in the model. In fact, anyway, so I know you understand what I am saying. So is there anything particular thing that you did to get out of the box samples, let's say, to overcome the limitations of a physical model?
So we haven't done what you call is what functional uncertainty quantification here. So that is a different area, and we do work on it, but in a very tractable small systems like Hilliard or like Alan Kahn. Those are like material science questions where we try to also incorporate like this, let's say even you have very nice differentiable model like neural network that can go in and first of all, it can learn the dynamics from your, let's say, just given PD system, which could be misspecified or incomplete, as you said, and sit in as a physical prior and do functional UQ on top of that. So it is possible to perform, but on this particular scenario, since the model itself is quite complicated, we chose not to take that route. And we just assumed the ETSM models, this Mali ice sheet model, whatever it gave is the ground truth. So we had to do like bunch of meta learning, go in the glaciology literature, and we check whatever we are doing makes sense compared to whoever else studied the Amery Ice Shelf. They might have used different model to simulate the same system or something. So yeah, it's a good question. It should be done, but it's quite infeasible and maybe not in US Department of Energy's interest right now to do so.
Yeah, yeah, Sanket. Let me check one more time if anyone is interested. Any question for Dr. Sanket?
Yes, sir. I have a
Yeah, go
question.
ahead.
Hello, Dr. Sanket. Uh,
Yeah, go ahead.
uh, Actually, I also work on Lambert-Amery Shelf, and the kind of work you're doing, I also try to do,
Yeah.
but I usually get failed. My question is related to the regime shift, like you are doing the future projection. So, in ISM, you use some kind of constant, like the friction constant. But when I'm applying the sliding law and I'm using the constant friction constant on T0, my output is good. But when I'm trying for the future projection, so C will change and there will be some effective pressure which C will gonna absorb. So for the future scenarios, I can't use the C like constant C. So how you tackle this problem? Because this is the problem which I'm facing and my model is collapsing.
Mm. That is a good question for the numerical model people, for the Matt Hoffman I reached out to as well when you asked me questions about how he tackled even the previous papers, Amery numerical simulations. I'll definitely ask him that and get back to you. But in here, we just use the same model, and I'm guessing they held everything else constant for like, and you're right, it will cause something like interesting, and that's why we want to make sure we cover every ground by using 100 trajectories and not just say like, oh, I have just 1 or 4 trajectories and I'm just going to do the value of information. So this uncertainty and uncertainties comes into play in there because we are not sure what could change. So we are taking in least drastic scenario and very drastic scenario as well. So I hope at least for the time being, it answers your question how we try to handle in this work. But the numerical model question, I would definitely have to ask my collaborator.
Regarding this issue, I tried some to do literature review and I found that if we are going to train our like physics-based model, so if you are trying to find new equation, the function-based equations, and we will try different kind of equation and we're gonna pick, okay, this is the particular parameter and this is the particular changing parameter we can replace instead of C. So we can get for the future scenarios. So, but I don't know how to run pin, so that's why I never tried that.
Okay, yeah, that's interesting. Yeah.
Yeah, thanks, Ketagya. Sanket, yeah, you want to respond, or I think that is right. I mean, it's a more on a numerical modeling question, not on the Bayesian.
Yeah.
Yeah. Okay. Yeah. No, I am interested, Sanket. One thing that let's say, I mean, when you were I listened that you generated the parameter space using Sobol algorithm. You talked about
Yeah.
what could have been done, let's say, Latin hypercube, or etc. But the thing is, see, you are assuming that 6 parameter space, 6D parameter space, that is to be constant over the entire simulation time or the projection time, whatever you call it, right? But what if the parameters are non-stationary during
Mm.
the emulation time? Then how your emulation will handle that situation?
I believe this stochastic simulators also have emulation cases, and I believe they also incorporate what is called nuggets and all. So there are ways to incorporate additional errors into your Gaussian process modeling. Since we didn't have a stochastic simulator itself, we did not end up using such. We are just assuming this is a deterministic simulator. These things are going to stay steady. If I rerun this, it will generate the same thing, and the parameters most likely are not changing. But I'll have to go back and ask the glaciologists whether their parameters are actually changing over time.
Changing. I also don't know. It just came to, yeah, that's true. True. And I mean, okay. And did you optimize eventually after in the emulator is set up?
What do you mean optimize?
So usually what we do once the emulator model is set up, the emulator model is basically association between the parameters and some kind of errors or etc. Right? But still, you have to find out from the large number of. But you are basically creating uncertainty, so you might not be. So basically, what we do in terms of finding a optimized emulator model. So you have created the emulator, which is still a default model. So which means it you put potato and French fry will come up. So you need to, like a normal model, you calibrate. You are still not calibrating the model to find out the optimal set of parameter. But here I don't think your objective is to find a optimal set of parameter. Rather, you want to generate a large number of parameters and eventually do the simulation, right?
And we also have to think it's just not deterministic emulator itself. It is kind of approximated in its own errors. The why we are choosing to use Gaussian process over just deterministic model for that reason itself. And even when we take the predictions out of it, they're actually predictions from its predictive distribution. So it's not just a predictive mean. We also incorporate the predictive variance that comes out of the Gaussian process emulator and sample out of that, so that we are like not just being bullish about what we are doing and making sure everywhere the uncertainties come into picture.
Yeah, I'm done. I'll take any other participant has any question. I'm just calling out few names in case just to check Maya or Sai, Jisha, Harini, anyone want to ask question, Abhirup, Chetan.
Maybe one small question from my end.
Yeah, Sai, go ahead.
Dr. Sanket, I would like to know how much information do you have on each of these 6 parameters before you begin this Bayesian analysis? Because I could see that the priors are quite well assumed before you run this analysis, maybe in the 9th slide that I was referring about.
Yeah. So this was, yes, definitely given to us by the experts from even the ranges. We went to one of the papers that had done extensive work on this glacier system and gave us like certain parameter ranges. So we chose to use those. And parametric form also was determined by the experts. And we also ran this, I believe, I don't have access to it right now, just using non-informative priors, where you only use like uniform distributions and see what is happening. It does end up constraining the parameters, but not as much as so if it would have used this already like known or expert-driven prior. So it does help in Bayesian inference if you start from a nicer expert prior if you knew it already. But if you don't, then you just have to run your chains very long and then see if they're converged, or maybe they will not get constrained as much just using the present day observables. Does that answer your question?
Yeah, I also suspect since the number of observations are quite less,
yes,
this is fair enough. Thank you, Dr. Sanket.
Thanks, sir. Thanks, sir. Any other question? Yeah. So I guess no other questions, Dr. Sanket. Thank you so much for joining. I guess it is very early morning for you at Brookhaven.
No, it's work
East Coast, right?
Yeah.
It's East Coast, yeah. So very nice having you, and I really like the presentation. And maybe we will also connect with you at a later time.
Yeah, and if any other questions, like let's say you have about numerical models or something that I'm not able to answer, I can definitely relate to Matt, who is like has worked in this area for 50-20 years or more. So just email me. I know Kritagya has like a bunch of questions about the numerical side, so I try to relay them to Matt as well. So yeah, reach out. Thank you.
Thank you so much, Dr. Sanket. You have a great day, rest of the day. Thanks again. We will close the call now.
Thank you. Have a good day.
Thanks.
Bye.
Bye.